Modern organizational strategy relies heavily on data analytics and artificial intelligence to project future volume and identify market trends. We feed historical data into algorithms to generate a mathematical probability of what will happen next. But this visualization shows the consequences of physical arrival. When a facility experiences an unpredicted surge, the system enters a state of chaotic, compounding failure. Generating a statistical prediction of an outcome is an entirely different operational problem than surviving that outcome. A static projection tells you how many units will arrive by Tuesday. It does not tell you if your loading dock has the square footage to process them when 3 trucks arrive at the exact same minute. There is a pervasive misconception in modern business that AI and predictive analytics are direct replacements for operational simulation. They are not. Static predictive models cannot account for cascading, time-delayed physical interactions. Relying on AI alone, without running those predictions through a constraint-bound testing environment, is a strategic liability. To bridge the gap between digital theory and physical reality, organizations use advanced simulation platforms like ExtendSim. This software provides a dedicated validation layer for digital transformation initiatives. The division of labor is precise. AI generates the operational hypothesis, and simulation provides the robust, physics-bound environment required to safely test it. Understanding this synergy requires looking at specific mechanical differences. We have to examine how discrete event simulation calculates time, and why parallel analysis is required to manage complex logistics. Modeling intricate systems in a risk-free virtual environment provides the exact parameters of failure. It is the only way organizations can safely foresee the physical impact of strategic decisions before committing real-world capital. The foundational challenge of systems engineering is accurately mapping time and sequential dependencies. If a process relies on a sequence of steps, any delay alters the timeline of every step that follows. This split-screen diagram compares a standard static spreadsheet model on the left against a continuous simulation timeline on the right. Standard spreadsheets calculate averages over fixed periods, meaning they completely fail to register dynamic, momentary time delays. Discrete event simulation, or DES, solves this by operating on a different mathematical framework. It calculates system states exclusively at exact points in time when an event actually occurs, rather than calculating fixed, continuous intervals. When a single disruption, like a machine breakdown, is inserted, the software recalculates the entire downstream workflow. This exact mathematical rigor is mandatory for modeling moving constraints. You cannot optimize a system if you cannot map how a delay passes from one sequential dependency to the next. Here, a single localized delay creates a compounding queue buildup further down the operational line. This time mapping translates directly to physical workflows. It shows exactly where a manufacturing line will stall, or precisely how a hospital patient flow will bottleneck during a sudden influx of admissions. Physical operations are inherently chaotic and entirely time-dependent. Discrete event simulation applies the correct mathematical framework required to capture that true operational reality. Once you establish how time and constraints behave sequentially, you can expand that perspective from a linear timeline to a macro-level network view of an entire organization. Look at this 3D wireframe of a complex supply chain network. Simulation software identifies exact friction points, like this red intersection, invisible in raw data dumps. Within this virtual model, engineers test new routing strategies, resolving the bottleneck and returning the system to maximum efficiency. Primary industry applications are massive, optimizing throughput in manufacturing facilities and routing around supply chain delays. These exact same virtual models are utilized across the transportation and energy sectors, allowing operators to improve resource allocation and meet strict sustainability goals by eliminating wasted motion. Creating detailed virtual models forces abstract, invisible data friction into the open, translating it into actionable, resolvable geometric problems. In the digital age, speed and scale are mandatory. Testing a single predictive model sequentially is no longer sufficient. Testing one what-if scenario reduces immediate risk. Running thousands of concurrent scenarios optimizes reality. ExtendSim fractures a single baseline model into dozens of concurrent tracks, analyzing multiple workflows simultaneously. This parallel processing evaluates multiple contradictory variables at the exact same time. By aggressively discarding failed models, it isolates the single most optimal strategy. This capability empowers businesses to respond rapidly to unforeseen market conditions or sudden structural challenges without resorting to trial and error execution. Massive computational speed and parallel scenario analysis eliminate the need to test new operational strategies in the physical world. However, this processing power exposes a distinct vulnerability present in all digital transformation initiatives. Simulation has an immutable limitation. Outputs are strictly bound by the quality and accuracy of the data they ingest. If you introduce corrupted inputs into the model, the entire sequence collapses. Building accurate virtual models requires deep expertise. Organizations must invest the time required to gather high-quality inputs and deploy skilled systems engineers who understand configuration. Feeding inaccurate data into a simulation platform yields confidently incorrect results. In advanced systems modeling, strict data integrity is an absolute non-negotiable requirement. When executed correctly, AI, data analytics, and simulation unite into one cohesive macro-level systems pipeline. This flowchart illustrates the sequential synergy. Raw data generates a statistical hypothesis. That hypothesis runs through parallel stress testing inside ExtendSim and outputs as a fully validated operational strategy. Predictive automation is driving modern digital transformation, but it remains entirely dependent on these robust testing grounds to prove its viability. Simulation platforms are the critical bridge connecting theoretical data predictions to practical physical execution. As systems engineering advances, integrating automation and highly detailed digital twins with simulation tools will create hyper-precise decision-making frameworks. The end result is a perfectly synchronized, highly efficient mechanical process, operating continuously without friction, delays, or physical bottlenecks. In a business environment defined by constant uncertainty, discrete event simulation provides the mechanical blueprint required for resilient strategic planning.